I'm going to talk about how to build a scalable multimedia search engine using Infiniband. This is a joint work with my group mates in NYU. These days, online search engines like Google and Bing provide search to multimedia information on the web. These online search engines must be scalable in order to ensure the low latency search on a huge data collections. Then how multimedia search is done? Generally, given a collection of images, the search engine first builds an index table for them. This procedure is usually done offline. The lowest of the index tables represents images, and the columns of the index table represents distinct features extracted from the images. Since there are billions of images and billions of features, the index table is absolutely enormous and is also very sparse. To process a query image, the search engine first extracts all the features from it, and then looks up the index table to find the images which contain those features. This is how search is done. Since the index table gets bigger and bigger as there are more and more images to search, in order to scale, we need to distribute the index table somehow. Then the question is, how are we going to do that? There are two ways to distribute the index. One is horizontally partitioned index. In this schema, each machine can be viewed as being responsible for a subset of being responsible for a subset of images and maintains a corresponding local index for them. To process a query, a coordinator first dispatches the query to all the machines, and then let each machine does a search locally. Finally, it aggregates the results from all the machines and returns the final answer to the user. Then this schema is widely used today. The main downside is that it is not scalable, since each query must be processed by all the machines. Then the search performance will do not increase as more machines and more data are added. Another way to distribute the index is vertically partitioning. In this, as the name suggests, we cut the index vertically such that each machine is responsible for a subset of indexed features. To process a query, the search engine needs to for example, to process a query with 1,000 features, the search engine needs to contact with 1,000 machines, which are responsible for those 1,000 features. As you can see, a search can be very expensive because a query may look up tens of thousands of features. But this schema is the upside of this schema is it is scalable, since the number of features being looked up is independent of the size of the index. The current wisdom is that vertical partitioning is impractical on the internet. Therefore, Liao. Existing search engines are almost horizontally partitioned. However, we believe that future data center network technology is going to change the design choice. Specifically, the technologies I am talking about is the ultra-low latency network. These networks, such as Infiniband and ROCE, RDMA on Ethernet, and these networks provide round-trip latency of several microseconds and order of magnitude faster than the Ethernet. In this talk, I'm going to show you that a vertically partitioned search engine works better on these networks. This is because we can use multi-run algorithms to reduce the number of lookups. And these multi-run algorithms are only practical on the ultra-low latency networks. Now, I'm going to introduce our VertiCut image search engines. It consists of two parts, offline indexing and online searching. To index an offline indexer, first it checks a set of features for each image using the well-known shift image feature extraction algorithms to generate a collection of 128 dimension feature vectors. It then maps these each high-dimensional feature vector to a 128-bit binary code using locality-sensitive hashing, which preserves semantic similarity. If two images are close to each other in the shift space, the timing distance of their binary code is small. To search for a query image, the search engine first transfers the query image to a 128-bit binary code, and then performs the k-nearest neighbor search in terms of Hamming distance. VertiCut uses the multi-index hashing algorithm to do the KNN search in binary space. Now I will introduce how it works. To index, this algorithm first breaks a 128-bit binary code into 4 disjoint pieces, and then index each part into a separate index hash table. Yeah. Since VertiCut performs vertical partitioning, these hash tables must be distributed among machines. But we don't shard the table ourselves. Instead, we use a DHT for this. Now, let's take a look at our VertiCut search architecture. The DHT we use is called PLAF, which is our preview works on the ATC. And this PLAF DHT runs on top of Infiniband and provided really fast lookups, for example, 10 microseconds. Then we stormed our four index tables into the PLAF DHT. And then, on top of PLAF DHT, we have a set of search nodes. When a query binary code Q arrives, it dispatches the query to one of the search node, and the search node does the k-nearest neighbor search using the DHT get to these index hash tables. Now, let me let me introduce how we do the k-nearest neighbor search in the binary space. To search for a query binary code Q, we first divide the code into 4 disjoint parts, and then performs the search iteratively with the increasing search distance. For example, in the first iteration, we find KNNs with Hamming distance with Q less than 4. First, we search each piece Qi in the corresponding hash table Ti, and in each hash table, we enumerate the indices whose Hamming distance with Qi is equal to 0, and then add all the items in those entries to a candidate set. After finishing the search on all the hash tables, we do a check. We check whether if KNN results whose Hamming distance with Q are less than 4. If it is, if yes, we stop the search and return the result to the user. If it is no, it's no, then we continue to find KNNs with Hamming distance less than 8. And does the same iteration search as the previous iterations. And the only difference is that we enumerate indices with indices whose Hamming distance with Qi is equal to 1, since the 0 we have already enumerated. After finishing the search in all the hash tables, we also does a distance track and change the distance threshold to 8. Then we can summarize our algorithms as this. For each search distance D, we run an iteration of search which contains 2 parts. First one, search each piece Qi in the corresponding hash table Ti independently, and then do a distance check. Now we can see why the reason why we cut the binary code into 4 pieces is to reduce the number of entries to be enumerated. However, this number of lookups is still enormous. Since the large, we notice that the large search distance D. Since we notice that the large search distance D will result in combinatorial number of lookups. Typically, in an image collection with 1 billion images, the average search distance D is equal to 20, which will result in 165,000 lookups in the DHT. Since the lookups are DHT lookups, it is very expensive. Therefore, our insight is to stop search as soon as the candidate set C is big enough. To do so, we remove the check in the red box, and then move the stop condition check into the search procedure in each hash table. And as soon as there are approximate fetch times KNN candidates in the candidate set, then we stop the search and returns the top K result. By using this optimization, we we greatly reduce the number of lookups in the DHT, which can be confirmed by our evaluation result. According to our experiments, we find that to obtain K results, we can stop search when the number of candidates is greater than 20 times K. Since when we choose the approximate factor to 20, the results of our approximate search will contain more than 80% of true KNNs, and the average distance of the result is close to that of true KNNs. The distance is remain less than 1, and it will reduce the number of lookups by a factor of 40. Okay. Then the second optimization we make is to avoid empty lookups. We find that there are more than 90% of lookups in the DHT returns empty results. Therefore, we build a bitmap for each hash table and replicate them to each search node, and only do a lookup in DHT after the bitmap returns a hit. Since the bitmap size is not that much big compared to the hash table size, and it does not increase with the number of images indexed, we can also use a blue filter to reduce the memory usage, and with a slightly increased query latency. Now we introduce our evaluation performance. We set up our experiments on 12 servers connected with Infiniband and use the 1 billion image descriptors from began dataset, and each query retrieves 1,000 KNNs. To demonstrate the scalability, we run a test with varying data size and varying number of servers, with each server always process fixed size of data, and we compared the query latency of two schema, the traditional horizontal partitioning, the black line, and our VertiCut partitioning, the green line. We can find that the query latency of the traditional horizontal partition schema increased rapidly due to the increased aggregation cost. Surprisingly, our VertiCut the query latency decreased in our VertiCut. This is because as the data size increased, the number of images in each hash entry also increased. To search for fixed K nearest neighbors, the number of entries we need to enumerate also decreased. This verifies that our VertiCut is scalable and effective on huge data collections. However, we need to notice that VertiCut is only feasible on low latency network. We compared our VertiCut on Infiniband and our VertiCut on Ethernet. We found that with the same number of lookups, the VertiCut on Ethernet is about eight times slower than VertiCut on Infiniband. And this is the result of the effects of optimization. And we can find that with approximate search, we improve the query latency by a factor of 50, and our VertiCut can achieve 550 times latency reduction. Related work, you can look into my paper, and now I make a conclusion that in this talk we verify that ultra low latency network allow VertiCut vertical partition to perform better than traditional horizontal partition. And in this paper, we present VertiCut, a scalable image search engine, which built on top of pilaf DHT and uses two optimizations to reduce the DHT lookups. And it will achieve better scalability and lower query latency than a traditional partition schema. Okay. Any questions? Not exactly. You say that.
Think about web pages. You have billions of web pages.
Yeah, right.
But effectively, the number of dimensions is probably, I don't know, order of 100.
Yeah.
Or not even now. So in that case, if you have a workload like this, you can't really do vertical partitioning. Because at some point, you will run out of. So if vertical partitioning at most, you can have as many machines as the number of columns. Right? Because vertical, you need to keep all these, all the value for a single column.
Yeah.
To be kept on a single cell.
No. Only need to be kept on a single hash table, not on a single server. It will use DHT. And
Okay.
yeah.
So effectively, you're doing like a mix of horizontal and vertical partition.
Yeah.
Okay. Okay. So this was my question. That in some cases, effectively, like narrowing the form globally is one of the important.
Yeah.
Okay. Any questions? I can go on forever.
Okay.
Yeah, you flashed the related work slide pretty quickly, but some of this reminds me of work that Ron Fagan was doing on, I think it was called optimal aggregation algorithms for middleware. The idea was that you had these objects and they had grades along different scales, I mean different criteria, and you were and they were distributed, and there was an issue about how many times you had to query each of the sources to get an overall optimal result. This has a lot of flavor of what you looked at. Did you consider that literature at all?
The related work we looked into is the high-dimensional distributed image search, the owning applications. And then next, in the future, we will need do other types of search, including text retrieval or other kind of search.
Okay, but this notion that you wanted to find, I mean, what you're trying to do here is you've broken your code into 4 pieces, right?
Yeah, right.
And you're asking 4 independent, Hamming distance queries.
Yeah.
These 4 pieces, and you're claiming that if I just stopped the search after looking at certain low values of D, I have a pretty good overall approximate result, right? So that's saying something about that the overall best result is actually tends to come from something that's good in all 4, or say at least one of the 4 quartiles, right, of this. And so that's of the same flavor. You've got 4 different sort of criterion under which you're evaluating nearest neighborness.
Yeah.
And they're distributed, and now you're coming up with an algorithm to sort of pull them all together. And your claim is that, I don't need an algorithm. I'm just going to look at the ones I get and cut it off from there, right? And it does pretty well on your data set. But have you looked at any of the more formal treatments of this, where you try to analyze just how well that does? Is there some property about the randomness of the LSH that allows that to actually work better than other types of settings? Does that make any sense? Right?
You mean that if we stop that earlier, the approximate the precision will not meet the requirement of the users, right?
That your approximation, do you have any analytical reason to believe your approximation is any good? You showed an experiment with a data set that showed, oh, when we do this optimization 1,
Yeah.
it ends up getting most of the nearest neighbors.
Yeah.
Do you have any analysis to back that up? Because some of these other papers have had analysis to look at these kinds of things. And I was just wondering if you looked at any of those papers in the analysis. We can take it offline.
Oh, we can.
Okay.
Okay.